So today, I will be talking about how to run audio and vision AI algorithms at ultra-low power. Before I dive into the solution, let's talk about the problem statement. Many of the IoT applications don't actually need full compute all the time. Of course, full compute drains the battery. What I mean by full compute is all the compute that's available. And let's walk through some of the example cases by what I mean by that. And let's talk about, suppose you have a security camera installed outside your home or your office looking outside on the street. You don't want the security camera to be running full compute on an empty street. You actually want an indication that there is something present there before you run the full compute. Similarly, if you have a human presence detection application like a laptop, you would not want to run the full compute on the solution to determine the human presence until you actually feel that there is a human there. Somebody there, something is there, right? Similarly, predictive maintenance, it goes on and on. One of my favorite is shoplifting applications. You don't want to be running a shoplifting application, full compute on it, till you know there's something in the aisle. And when I talk of something of this sorts, I just feel that once you're able to develop these applications that are running on battery, these are low cost, you can throw them around. And somebody might say shoplifting application might be connected to power supply, but not really, right? We would want to, at Synaptics, we want to enable these small little devices that you can just throw around in the store, for example. So with that background, what we want to talk about is how do you run these applications at ultra low power? And I kind of, I've given away the hint is, we don't want to run the full applications. That's the solution. And so this is sort of a summary of what we were talking about. I gave a block diagram, very high-level block diagram of the silicon solution. This is yet to be released. So take a picture. It's okay. Slides will be there anyway. So what I'm going to talk about is, it's a multi-stage hardware. And the stage one is an always-on, ultra-low power in single-digit microwatts of power consumption. Stage one wakes up the stage two, which is a little bit higher efficiency or higher compute than the stage one, and then the stage two wakes up the stage three, which is the full compute. Now, you can imagine that these stages waking each other up, and while the stage two and stage three remain in deep sleep to really save power, that means you need a tight orchestration of software, and a software that doesn't fail. If the software fails, you're looking at an unresponsive device, not waking up the main compute, or waking up the compute all the time, and you don't have any power advantage there. So it needs a very tight orchestration of the software. And I'll show you some more details about it, and we'll see when I talk about more of the hardware components. The models play, like Eric mentioned, models play a very, very critical part in enabling this solution.